Welcome to the fourth video of our example problem. In this one, we'll go through the shear stresses it experiences. These will be due to both lateral loading and torsion. Now that we've determined the normal stresses due to our loading at point H, we need to find the shear stresses at point H. So there's going to be two sources for that. There's going to be our normal sort of conventional lateral shear, and we're also going to have shear from torsion, because we've got a little bit of torsion going on from this 10 kilonewton force right here. So let's start though with the lateral shear in the x direction. So the normal lateral shear resulting from this 10 kilonewton force. There's also going to be torsion from it, but there's going to be just shear from this. And so lateral shear, and this is going to be in the x direction, so we'll call it yx, and that's going to be equal to vq over I t, which is going to be equal to, well, 10 kilonewtons. That part's easy. Q, we already determined what Q was earlier. We said it was 27,684 millimeters cubed. And we'll be dividing that by our second moment of inertia, which was 2,092,753 millimeters to the fourth. And now this one is going to be, well, let's say it's 2 each times 6 millimeters, because it's a circular cross section. So when we're applying this shear and we're looking at this cross section, half it's going to go through here, half it's going to go through here. Okay, so we've got 2 times the thickness. So don't forget that the thickness here is 12 millimeters, not 6 millimeters, and that's going to give us 0.011 pascals. Now let's look at the lateral shear in the other direction, in the YZ direction. So this is from the force we had in the X direction. We don't have any force in the Z direction, and that's just as well, because Q would be 0 there anyway, even if we did have a non-zero force for V. So we've got that. Now let's look at the torsion. Now, torsion, it's going to be in the YX direction, and it's going to be equal to the torsion times the radius at the point we're considering, and that's going to be, well, we'll call that rho, I guess, divided by our polar moment of inertia J. And that's going to be, what did we say the torsion was? 2,000 kilonewton millimeter times 51 millimeters divided by 4,185,506 millimeters to the fourth. And that's going to give us 0.02437 megapascals. It's been a little wild there. I'm putting just a whole bunch of, I don't know why I put all those. So when we're looking at that, we're going to have to check at point H, the torsion, or the shear due to the lateral shear is going to be in this direction, and the shear due to torsion is also going to be in this direction. So we're going to have to sum those together. Those are going the same direction. Very good. So now we've got the shear stress as well. It's time to figure out what our actual shear state is. Let's do that in the next video.